In this video, we will talk about Stokes' theorem, which relates the curl of a vector field over a surface to the line integral over the boundary of the surface. We have two overview slides. This is the first slide, and we have this second overview slide, which is essentially a big example that we have. We will spend about 5 minutes going over this overview slide, and then we'll go through each topic in more detail and with more examples. Our first topic is Stokes' theorem, which relates the surface integral of the curl of a vector field to the line integral of that vector field. We have a physical interpretation that while the tendency to rotate will vary from point to point, Stokes' theorem says the collective measure of this rotation, measured by the curl, taken over the entire surface, is equal to the tendency of the fluid to circulate around the boundary curve. We have this additional theorem that says, that comes from Stokes' theorem, that if the curl of a vector field is zero everywhere, the field is derivable from a scalar potential. That is, if the curl of A is equal to 0, then there exists a scalar function such that A is the gradient of the scalar function. In order to work with Stokes' theorem, we'll have to review first how to do the surface integral of a vector field, and then how to do a line integral of a vector field. So we'll review surface integrals of a vector field and line integrals of a vector field. And additionally, we'll review the Jacobian that's used when we change coordinates from cylindrical and spherical. And then one other thing we need to learn but not review is calculating the boundary of a surface. So it turns out if phi is our mapping from a domain to a surface, remember we consider a surface a mapping from something in the UV or the XY plane in two-dimensional space, then it gets mapped to three-dimensional space, and that's done by this mapping or parameterization phi. So if phi maps a domain to a surface, then it will also map the boundary of the domain to the boundary of the surface. And that'll give us this C, the curve C here, because this curve C is related to this surface by being the boundary of this surface. And last, we'll do 4 examples, 2 of them in lots of detail, longer than they probably should be, and the other 2 are very quick. The first thing we have is this formula here for Stokes' theorem, which says that the surface integral of the curl of a vector field A is equal to the line integral where the curve that we're integrating over C is the boundary of the surface S. So it's the line integral of that vector field. And this way, I'd say that the curl of a vector field over the surface is related to the line integral over the boundary of the surface. And one physical interpretation is, while the tendency to rotate will vary from point to point, Stokes' theorem says the collective measure of this rotation taken over the entire surface is equal to the tendency of the fluid to circulate around the boundary curve. A theorem that comes out of Stokes' theorem is that if the curl of a vector field is 0 everywhere, the field is derivable from a scalar potential. That is, if the curl of A is equal to 0, then there exists a scalar function phi such that A is equal to the gradient of phi. 2 things. The line integral of this type of a vector field is always independent of its path and therefore is called conservative. Another name for this type of field is a gradient field, since this field A is the gradient of some other scalar function. There are 3 things we should review before we dive into Stokes' theorem. I won't do examples here of these 3 things because we'll see plenty of examples as we work through Stokes. So here is Stokes' theorem, and first, since we have this surface integral on the left-hand side, I want to remind you of how to take a surface integral of a vector field. So if V is our vector field and S is our surface that we're integrating over, the first step is to parameterize our surface S and determine its domain. Remember, our surface is in 3-dimensional space. Our domain is in the 2-dimension, in the UV or the XY plane. The second step is to write our vector V vector field V in terms of our parameterization. And the reason why we do this is V is defined over the whole entire space, but we're only concerned with V over our surface. So we parameterize it. We do a composition, V composed of our surface. The next thing we do is to calculate the norm of our surface, a vector normal to our surface. And we do this by looking at the parameterization of our surface, calculating the partial derivative with respect to, remember this is a two-dimension, our first variable of our domain, crossed with the tangent vector, which is the partial derivative of our parameterization with respect to our second variable. And then last, we plug these components into this formula here. Next, we'll review the line integrals of vector fields because this is the right-hand side of Stokes' theorem over here. So if you look at this procedure, it's actually very similar, analogous to the surface integral procedure. So take a moment to compare them. But the first thing you want to do is to parameterize your path, and it's just going to be dependent on one variable. We think of a path as traveling along some curve. So over time, the C of t gives you where you are on the path, and then as t varies, you get the entire path. The next thing we do is calculate the derivative, which is like calculating the tangent, which is a lot like calculating this normal over here for surface integral. The third step is we calculate f composed of c, much like we did here for the surface integral. So the vector field is defined over the entire space. So what we want to do is narrow down or compose our vector field so we're only looking at the vector field as it pertains to our path. And then finally, we plug in these three components into this formula. The last thing to review is the Jacobian, which we had talked about in our last video about Gauss's theorem. So the Jacobian is used when you change from one coordinate system to another, and it represents the transformation of one unit volume in one coordinate system to another. And this is the formula in general if you're translating from the XYZ coordinate system to the UVW system. It's this determinant here. And we calculated this for a transformation from rectangular to polar and also rectangular to cylindrical, and we found that the Jacobian is equal to R. And we also calculated the Jacobian when we go from rectangular to spherical, and we actually got negative rho squared sine theta, but for the correct orientation, we take the positive version of that, so that's rho squared sine theta. Now that we've gone through this, we're ready to do some examples. And we will start with this example here that was our second overview page. The question is, let S be the parabola z equals 9 minus x squared minus y squared, that's this shape here, defined over the disk in the xy plane. Verify Stokes' theorem for the vector field F equals 2z minus y, x plus z, and 3x minus 2y. And before we start doing this problem, and I'm going to do this, when we say verify Stokes' theorem, we're going to do the calculation using the left-hand side formula as well as the right-hand side formula and verifying they're equal. But before I do that, I just want to see how I got an image of this paraboloid. And this paraboloid here is related to z equals x squared plus y squared. And if you recall, so this is a three-dimensional surface, right? We have two variables, it gives us a height, so 3 dimensions. What we would do to graph three-dimensional surfaces is often we would look at level curves. We would set z equal to a constant and see what the shapes would give us. So here I set z equal to 1, 4, and 9, and we see that these level curves are circles of radius 1, 2, and 3. So now I can come into three-dimensional space and think, oh, also when z is equal to 0, we just get the single origin point. And then this circle, I will raise it to a height of z equals 1. So that's here. As my circles get bigger, the heights increase. So you kind of have this bowl shape. And now what happens is since I have 9 minus this bowl shape, it inverts it. And we get this shape over here. And now we can continue on to the problem of verifying Stokes' theorem by calculating, we'll start by calculating the left-hand side of the equation. And the first thing I'm going to do is do my cross product. So my del cross f is going to be my ijk, directions dx, dy, dz, and then I'll have 2z minus y, x plus z, and 3x minus 2y. When I do this calculation, I'm going to get the vector -3, -1, 2. And what I often do is then I circle this vector field f and I put an arrow to the curl, so when I come to plug it into my integral, I don't accidentally plug in f, because I'll be looking for a vector field and I'll see this and then I'll plug it in. But really I want this one. I'm going to integrate the curl, not the function. The next thing I'm going to do is parameterize my function. And if you recall, for our surfaces, when we have the surface expressed as z equals 9 minus x squared minus y squared, that's simply xy and then my 9 minus x squared minus y squared. X goes between -3 and 3, and y, because it's the circle here, when z is equal to 0, will go between negative square root of 9 minus x squared and positive square root of 9 minus x squared. Next, I compose our function, our vector field, with our parameterization. So I'm going to plug in our parameterization x, y, 9 minus x squared minus y squared into f. So then I look at f, my function f is my vector -3, -1, 2. So actually my assignment for f doesn't depend on x, y, and z. It's always -3, -1, 2. To calculate the normal to our surface, I'm going to calculate the partial derivative with respect to x of our surface. So with respect to x, that's 1, 0, and minus 2x. Partial derivative with respect to y, I have 0, 1, and minus 2y. I take the cross product of my partial derivative, my tangent with respect to x, tangent with respect to y. That will give me my normal, and that's equal to 2x, 2y, 1. And now we are ready to plug in to our surface integral formula. And our surface integral, again, is over a domain, so it's a double integral. Our domain here is where our surface, our paraboloid, intersects the xy plane. So it's the circle of radius 3. So our x-coordinate goes between -3 and 3. Our y-coordinate for the circle goes between negative square root of 9 minus x squared to positive square root of 9 minus x squared. And then we take our field over here, which we composed already. So we have our -3, -1, 2. And then finally we dot it with our normal, which is 2x, 2y, and 1. And certainly it's okay to integrate this, but I decided I wanted to use polar coordinates because of the circle here, which means that I'm going to convert x to be r cosine theta, y to be r sine theta, and r to go between 0 and 3, and theta to be go between 0 and 2 pi. And this will give me my circle. Actually, it's not my circle, but my disk of radius 3. And just to remind you that the Jacobian, we need to multiply by the Jacobian since we're transforming from rectangular coordinates to polar coordinates. And my Jacobian is equal to r for polar coordinates. So my integral becomes r goes between 0 and 3, theta goes between 0 and 2 pi, and then I have my -3, -1, 2. My 2x becomes 2r cosine theta, my 2y becomes 2r sine theta, and my 1 remains 1. I do my dot product, and I get my integral of -6r cosine theta minus 2r sine theta plus 2. And if you do this integral, you get 18 pi. So the work I've just done was to integrate the curl, so I calculated my curl, over the surface, and the surface over here. And the integration over surface is a double integral over the domain. And here's my double integral. The next thing now that I have to do is the right-hand side, which is the line integral of dr, and I just dotted it with my vector field f. Next, I want to calculate the right-hand side of Stokes' theorem for this vector field and this surface. So I'm going to take the line integral of our vector field using the curve is going to be the boundary of the surface. It's not hard to see here from this drawing that the boundary is this circle, 9 equals x squared plus y squared, but there is a formula that I wanted to show you that you can use when it's not so obvious what the boundary is. This is the formula. I'm using this delta to signify boundary. So when I say delta of a surface, we're talking about the boundary of the surface. When I say delta of a domain, that's the boundary of the domain. And the idea here is if this phi is the mapping from the domain to the surface, that's our parameterization, right? It goes from the UV plane into the surface, or the 2 dimensions into 3 dimensions. What it does, it'll also map the boundary of your domain into the boundary of your surface. So phi maps the domain to surface, and it maps the boundary of the domain to the boundary of the surface. In our example here, then the boundary of the domain, and our domain is this disk, everything in yellow. So the boundary of the domain is the circle, 9 equals x squared plus y squared, and I express this in polar coordinates. Then when I take phi, well, I need my mapping phi, and we talked about the mapping phi when we did this left-hand side of the equation. When you're given a surface where it's z equals some function of x squared, y squared, your mapping is going to be your xy, and then you're going to have your xy, and then naturally z is going to be your function, 9 minus x squared minus y squared. And we need to complete our parameterization by saying our limits of x and y. So x goes between 0 and 3, and y goes, and it's the circle. Negative square root of 9 minus x squared is positive square root of 9 minus x squared. So now when I want to calculate this phi of 3 cosine theta, 3 sine of theta, I plug this into my phi. My x is my 3 cosine theta, my y is my 3 sine theta, my z is going to be 9 minus x squared, which is 9 cosine squared theta, and then minus y squared, which is minus 9 sine squared theta. This here becomes 0. So now my curve is simply 3 cosine theta, 3 sine theta, 0, which is exactly what we were guessing it was going to be, this circle here of radius 3. I'm just going to kind of reduce this calculation over here just to give myself more space. I rewrote my parameterization of c. I just brought it down here along with my limit for theta. Theta is going between 0 and 2 pi. And now I can also take the derivative of my c, and that's minus 3 sine theta, 3 cosine theta, 0. And then I can compose my field, my vector field, with c. So that's going to be f composed of 3 cosine theta, 3 sine theta, and 0. And my f is 2z minus y, z is 0. So I have my minus y, minus 3 sine theta. I have my x plus z. My z is 0, so I'm just left with x, which is 3 cosine theta. Then I have 3x minus 2y. So 3x is 9 cosine theta, minus 2y is minus 6 sine theta. And now I'm ready to plug into my formula for my line integral. No, this is my formula for my line integral. I'm integrating from 0 to 2 pi. I have my f of c, which is f of c is minus 3 sine theta, 3 cosine theta, 9 cosine theta minus 6 theta, dotted with my derivative of my path. So that's minus 3 sine theta, 3 cosine theta, 0. Do the dot product and the integration, and you end up with 18 pi. And what we have just finished is integrating f over the boundary of the surface, which was our line integral. And so you can see for both sides of the equation, we got the same answer and therefore have verified Stokes' theorem for this example. In our next example, our vector field is y e to the z, x e to the z, xy times e to the z. Show that the integral of v around the oriented simple closed curve C, that is the boundary of a surface S, is 0. We assume S is the graph of a function. Here is my Stokes theorem. I just reversed the left and the right-hand side. And what I'm going to do is I'm going to use this curl side of the function. I set up my curl for the vector v, that's ijk, ddx, ddy, ddz, y e to the z, x e to the z, xy times e to the z. I start with the I direction, taking the cross-multiplying and the partial derivatives. ddy is x e to the z, minus ddz will be x e to the z. In the j direction, I have ddx, which is y e to the z, minus ddz, which is y e to the z. And I should have put a minus sign here, but it's okay, they'll cancel. And finally, in the k direction, I cross-multiply. Derivative with respect to x is e to the z, derivative with respect to y is e to the z. And what you see is my curl is equal to 0, 0, 0, which then means this side of the equation is equal to 0, which means that the right-hand side is equal to 0. That is, the line integral over the vector field over c is equal to 0. And a couple of comments. One, the reason why I chose the curl, and a big hint to choose the curl side of Stokes' theorem, is that in here there's not enough information to parameterize your surface, so it'd be really hard to do the surface integral. The second thing is that if a problem mentions Stokes, sometimes I just calculate the curl just to see if I get a 0, because that'll simplify a lot of things. Similarly, if a problem mentions Gauss, I might calculate the divergence, hoping to get a 0. This next problem is to use Stokes to evaluate the line integral negative y cubed dx plus x cubed dy minus z cubed dz, where c is the intersection of the cylinder x squared plus y squared equals 1, that's this black cylinder, and the plane x plus y plus z equals 1. The orientation on c corresponds to the counterclockwise motion in the xy plane. The first note is hopefully you saw the vector field here buried in this is minus y cubed, x cubed, minus z cubed. The next thing is we want to be able to draw our cylinder and then the plane, and we want to know what does the intersection of the cylinder and the plane look like. I have this drawing here for you so you can see it's an ellipse, but my first attempt at drawing the intersection, I guess I had thought it was going to be this, because I imagined it this way. I thought it was going to be a parabola, but then I did the math and I saw that the parabola wasn't it. And so here is what I looked at. Our cylinder was x squared plus y squared equals 1. Our plane was x plus y plus z equals 1. So I looked to see what their intersection is. So I set them equal. My x squared plus y squared was equal to my plane, x plus y plus z. And from there you can see algebraically what I have is this ellipse here. So x minus 1/2 squared plus y minus 1/2 squared equals z plus 1/2. But I actually don't need this equation, but I do have the ellipse. Looking back at the problem then, we wanted to use Stokes to evaluate the line integral. So when someone says to me, use Stokes to evaluate the line integral, I assume they want me to use the other side of the equation. So the other side of the line integral equation is the surface integral. So I wrote down, this is the side I assume they want to use, and I wrote down, or I copied here, my surface integral formula, but I plugged in my cross product, my curl, in for my vector field. And the reason why I assume they want this side of the equation is if they just wanted me to use the line integral side of the equation, they probably would have said evaluate the line integral. But because I said use Stokes, I assume they want the other side of the equation. And the first thing when I have Stokes, often when I have Gauss, is I go ahead and I do my cross product or my divergence, hoping to get a 0. But here's my vector field. So I have ijk, ddx, ddy, ddz, my minus y cubed, my x cubed, my minus z cubed. When you do the cross product, you'll get 0, 0, 3x squared plus 3y squared. And again, I'm going to circle this part here, and I want to remember I'm using my cross product, my curl. Now I need to parameterize this surface that that is the part of the plane that intersects the cylinder. So the trick is to realize that even though it's kind of this oval shape, and by oval shape I mean also the interior, the surface is this interior kind of oval shaped thing, it is actually the plane that intersects the cylinder that is the surface, but it's the part of the plane that's above the bottom of the cylinder. So the parameterization of my surface is the plane, which is, and the plane is, the equation z equals 1 minus x minus y. So the parameterization is xy, and z is equal to 1 minus x minus y, but it's just the part of the plane where x goes from -1 to 1, and y goes from negative square root of 1 minus x squared to positive 1 minus x squared, positive square root of 1 minus x squared. So it's just the portion of the plane above the circle. So this is the tricky part of this problem. And now I can compose my vector field, with my parameterization. So that's f composed of x, y, and 1 minus x minus y. My vector field is over here. So the first element of my vector field is 0, the second is 0, and the last is going to be 3x squared, so that's 3x squared, plus 3y squared, so that gives me 3y squared. I can also compute my normal vector to my surface by taking the partial derivative of my parameterization with respect to x, that's going to be 1, 0, and minus 1. Partial derivative with respect to y is 0, 1, minus 1. I compute the normal and I get 1, 1, 1. I am going to need some more space, so I am going to go ahead and reduce this here. I am ready to plug into my integral formula. So it's a double derivative over the domain. So I get, where's my x goes between -1 and 1. My y goes from negative square root of 1 minus x squared to positive square root of 1 minus x squared. So again, so this is dy, this is dx, and then I need my vector field composed with my parameterization of my surface. So that's over here. So I get 0, 0, 3x squared plus 3y squared. And then I dot it with my tangent vector, which is 1, 1, 1. So what I get is this integral here, integral from -1 to 1, integral from negative square root of 1 minus x squared to the positive square root of 1 minus x, that should have been a squared, dy dx, 3x squared plus y squared. And at this point, I'm going to change to polar coordinates using x equals r cosine theta, y equals r cosine theta, and the Jacobians equal to r. So what I have is the integral from 0 to 1, that's my limit on r, 0 to 2 pi is my limit on theta, and then I have, where is this? I have 3x squared plus y squared, so that's simply 3r squared. And then I also need to multiply by my Jacobian r. So that's going to give me 6 pi 0 to 1 dr r cubed, which is 6 pi 1/4 r to the 4th evaluated at 1 and 0, which gives me 3/2 pi. I know I had told you that when I use Stokes to evaluate the line integral, that means they want you to do the surface integral of the curl. But for the sake of completeness, I'm going to do this entire problem again using the line integral. I'm going to be using this left-hand side, the line integral. So I've copied down my line integral formula, substituting my v for my f, since this is the name of my vector field. So it's a to b, my vector field composed of my curve, and then the derivative of my curve. And the next thing we need to do is think about parameterizing this curve. And so that will be this blue ellipse here. And I'm going to start with this formula here, which talked about finding the curve that's the boundary of a surface S. And the way we do that is we look at the boundary of the domain of S, and then we map it with phi, the mapping that goes from the domain to the surface. So in other words, if phi maps the domain to the surface, it'll map the boundary of the domain to the boundary of the surface. So as I discussed before, the surface we are mapping is actually the portion of the plane that intersects the cylinder. Well, we have the equation for the plane, which is x plus y plus z equals 1, or in other words, z equals 1 minus x minus y. So to parameterize our surface, that would be xy is mapped to xy, and then z is equal to 1 minus x minus y. But the trick is we don't want the whole plane. We only want the plane that intersects the cylinder, which is the same thing as saying we only want the part of the plane that is above this disk, that is above the domain. So the disk being x goes from -1 to 1, and y goes from negative square root of 1 minus x squared to positive 1 minus x squared. So here we have the parameterization of our surface. Now that we have the parameterization of the surface, if we want to find the curve C that our line integral is taken over, then we need to find the boundary of the surface. But the boundary of the surface is phi boundary of the domain. The domain is this yellow disk, so that means the boundary of the yellow disk is this circle here. So to find C, we're going to, well, first, let me parameterize the boundary of the domain, which is the circle. So that's just r cosine theta, r sine theta, where r is equal to 1, because this is just the circle of radius 1. And we plug that into phi in order to get the boundary of our surface, which is our curve that we integrate over. So plugging r cosine theta, r sine theta into our mapping phi, we have the first coordinate is x, which is r cosine theta. The second coordinate is y, which is r sine theta. And the last coordinate is 1 minus x minus y, which is 1 minus r cosine theta minus r sine theta. As I mentioned, my radius is equal to 1, so I went ahead and plugged that in, and I rewrote out the parameterization of my curve. C is equal to cosine theta sine theta, and then 1 minus cosine theta minus sine theta, where theta goes between 0 and 2 pi. Now I can take the derivative of my curve because I will need that in my integral formula over here. So I have minus sine theta, derivative of sine is cosine theta. The 1 goes away, I'll have sine theta minus cosine theta. So this is my derivative. So next I can do v composed of c. My v is over here. It starts with minus y cubed, which is minus sine cubed. The next term in v is x cubed, so I get cosine cubed. And the last term, unfortunately, is minus z cubed, unfortunately because it's kind of long. 1 minus cosine minus sine cubed. And now I am ready to plug into my integral formula from 0 to 2 pi d theta of my composition here, minus sine cubed, cosine cubed, 1 minus cosine minus sine cubed, dotted with my derivative, minus sine cubed minus sine theta, cosine theta, sine theta minus cosine theta. I do my dot product, and then I started to do my integration. I didn't have room for everything, but I will tell you I did use some of these double angle formulas, and eventually I got to 3 pi over 2, which if you look back is the same answer I got when I did this using the surface integral. I have one more quick example. Let S be the surface shown over here, and let V be the vector field y minus x e raised to the xz. Use Stokes' theorem to evaluate the surface integral of the curl of V. So the curve, which is the boundary of the surface, is the circle of radius 1. So I parameterize that as cosine theta, sine theta 0, where theta goes between 0 and 2 pi. Now my V composed of C is my y, which is my sine theta. Then I have negative x as my second coordinate, which is negative cosine theta. And as my third coordinate, I have e raised to the xz. So fortunately, z is equal to 0, so e to the 0. So this becomes sine theta minus cosine theta and 1. My c prime is minus sine theta, cosine theta 0. So now I can set my integral 0 to 2 pi d theta. My v of c, which is sine theta, cosine theta 1, dotted with my c prime, minus sine theta, cosine theta 0. So I integrate from 0 to 2 pi. I do my dot products of my sine squared, cosine squared, and actually this should, oh, here's a minus. So I get a minus 1 here. When I integrate, I get minus 2 pi. To review what we have covered in this video, we have considered Stokes' theorem, which relates the surface integral of the curl of a vector field to the line integral over when the curve for a line integral is the boundary of the surface. The next thing we did is we looked at this theorem that said if the curl of a vector field is 0 everywhere, the field is derivable from a scalar potential. That is, if the curl of A is equal to 0, then there exists some scalar function such that A is equal to the gradient of that scalar function. We said the line integral of this type of vector field is always independent of the path, and for that reason it is called a conservative field. Sometimes it's called a gradient field, since it is the gradient of a scalar function. We reviewed how to do surface integrals of a vector field, and we also reviewed line integrals of vector fields so that we could calculate both sides of Stokes' equation. We reviewed the Jacobian, which is a measure of how a coordinate transformation affects a unit sphere. For polar coordinates and cylindrical coordinates, it's equal to r. For spherical, it's equal to rho squared sine theta. And I also, in this video, had given you a formula to calculate the Jacobian in case you have some other transformation you would like to do. We calculated the boundary of a surface, which we needed here, since we were relating the surface integral to the line integral, where the line is the boundary of the surface. So we said if phi is the mapping that goes from the two-dimensional domain to the three-dimensional surface, then phi of the boundary of the domain maps to the boundary of the surface, and the boundary of a surface is a curve. And last, we did several examples. And that's it for this video. Thank you for watching.